And we're back once again. We're going to talk more about thermodynamics today. Specifically, I want to get into some of the meat and potatoes of thermodynamics and some of the real important concepts here. So we're talking about the ideal gas law. So the ideal gas law we can write as PV equals nRT, where P is pressure, and that's going to be measured in pascals. V is volume. Now here's a big difference from chemistry. In physics, we like to use SI units, whereas in chemistry they don't. They like to use liters or some nonsense like that. We're going to use meters cubed because that's the SI unit. For volume is length by another dimension of length. So it's going to be meters cubed. N equals number of moles, which is going to be directly proportional to the number of particles. R is the universal gas constant, which we'll talk about in a minute. So I guess this one has units of moles. Universal gas constant has units of joules per mole Kelvin. And then finally, temperature. Which is in Kelvin. So if you guys have taken chemistry before, you guys are probably familiar with this law already. And this isn't going to be too different from what you've done before. So what we can take from here is that your number of moles should be constant. I mean, you can change the number of moles. Most of the time we're going to say that's constant. Most of the time we're going to say if you got a container with a fixed number of amount of gas in there, if you have gas leaking out, then things start to get kind of weird. But I mean, that's something that we'll predict too. So R should be a constant always, and then everything else can change. But most of the time, moles will be constant, but it's allowed to change. So what we could do is we can actually say, let's solve this for R. So I can say PV over NT equals R, or we could have said PV over T equals NR. So PV over NT equals a constant, right? So that allows me to do something where I care about ratios and comparing things to each other. So I could say, like, the first time I look at the gas, I can say P1 V1 over N1 T1 equals P2 V2 over N2 T2. And like I said, most of the time this N is going to be constant, so you could just cancel that out. So this is going to be all of those things you learn in chemistry, Avogadro's log, Gay-Lussac, all those ones are going to be encapsulated in this relation. I don't actually memorize all the other ones because I just go to the ideal gas law and figure it out from there, because, I mean, why would you memorize more than one thing if you don't have to? So, yeah, for the ideal gas law, most of the time we're going to do something like, say, you've got a container at standard temperature and pressure. So we're going to say, so if we say standard temperature and pressure, then that means temperature is 273 Kelvin, pressure is 101,300 pascals, because that's atmospheric pressure. So if you're at sea level on Earth, that's what the pressure is ish. I mean, of course it varies. And then you have, let's say you have 1 mole. I want to know what volume does this gas take up? Oh, I need to talk about the universal gas constant. So the universal gas constant, like I said, is just a constant, and its value is going to be 8.314 joules per mole Kelvin. Okay, so what volume does our gas take up is what we're looking for. That's the goal. Well, to do this, I just I mean, this is a put numbers into equation thing, right? So I say, starting with PV equals nRT, I say V equals nRT over V, or over P, my mistake. So then it's going to be 1 times 8.314 joules per mole Kelvin times 273 Kelvin over your pressure is 101,300. Now, if you put this into your calculator, I'm going to pause it while I do it. Now, those of you who are have taken chemistry should expect what's coming already. So let's finish up my units here. This should have been moles here. Then you should know that any gas at STP will take up 22.4 liters. Technically, we get 22.3 liters here, but because STP really supposed to be 273.15. So that's going to be a small difference here. But actually, this is not what we get from our equation, though, because, like I said, we're doing this in pascals, or newtons per meter squared. We are doing this in SI units. So what you're actually going to get out is going to be 0.0223 meters cubed, which is just a little bit different. I mean, it's conceptually it's the same thing. It still means the same amount of space taken up, but what the difference is, I mean, it's in SI units. So there are 1,000 liters in 1 meter cubed. Okay, so there are a couple of points that we want to make sure we make on here to really make sure we know what we're talking about with the ideal gas law, because this is an ideal law. It is not a perfect law. It's not a perfect system. This is what we use for approximations and making our lives easy. So let's go ahead and actually flip the paper over and talk about assumptions we make.